Welcome to Monochemistry. In this lesson, we're going to have an introduction to nuclear chemistry. Nuclear chemistry is probably one of the scariest prospects for an AP chemistry student in that it's so different from the other chemistry that we learn. It brings to mind perhaps horror stories of radioactive monsters like Godzilla or death and destruction in the atom bomb. But in reality, nuclear chemistry is something that happens on an everyday basis and is very beneficial to both humans and to the world around us. So let's learn a little bit more about nuclear chemistry and maybe you won't be so afraid of it from now on. It's important to note that there are two types of naturally occurring radiation. Or, if you prefer, there are two types of naturally occurring nuclear reactions. The first type is called radioactive decay. In radioactive decay, an unstable nucleus emits particles or electromagnetic radiation spontaneously so that they can become more stable. In nuclear transmutation is the result of the bombardment of a nucleus by particles like neutrons, protons, or other nuclei. This results in a change in the original nucleus. Both of these reactions occur naturally in the environment. What are some of the differences between a chemical and a nuclear reaction? Probably the most substantial difference is that the elements in nuclear reactions are often converted from one to another. That never happens in a chemical reaction. In a chemical reaction, we form bonds and we break bonds, but we don't change one element into a completely different element. That's why a lot of chemistry students think this is scary, because it's like magic. But it's not. The second most important thing to note is that in chemical reactions, the only kind of transfer of particles we see are electrons. But in nuclear chemistry, it can be protons, neutrons, electrons, and other particles that I'll introduce you to here in a minute. The third substantial difference is that extremely large amounts of energy are transferred during nuclear reactions, whereas relatively small amounts are transferred during chemical reactions. And fourth, the rate of a nuclear reaction is not affected by the typical factors such as temperature, concentration, pressure, catalysts, whereas chemical reactions are significantly affected by those factors. Here are some common nuclear chemistry particles and their notation. So we have an alpha particle, which is actually a helium nucleus. And as you can see here, it's written as either a helium nucleus with a 4-2 or an alpha particle. That's what A stands for there, alpha particle 4-2. Now what does the 4-2 stand for? If you think back to your chemical notation that we learned about earlier in this course, then you know that the 4 is the mass and the 2 is the atomic number. So a helium nucleus would have 2 neutrons and 2 protons, and therefore would have a mass of 4. The alpha particle is exactly the same, it's just a slightly different notation. Either one of these is acceptable, but you have to be able to recognize both. Beta particle, which is an electron. Now, an electron has a mass of 0, as we've discussed. It has an atomic number of -1, which is a bit different than maybe what we've talked about before, so get used to that. Now, gamma radiation has no mass or atomic number. It's simply radiation. It's electromagnetic radiation. It's energy. So it doesn't have mass or atomic number. A neutron, on the other hand, as you know, has a mass number of 1, but it has no atomic number because a neutron is not technically classified as something that can change the atomic number, whereas a proton would be. So a proton, also known as a hydrogen atom or nucleus, has one proton and therefore has a mass of 1, or you can write it as a p. Notice there are no charges really associated with these. Now a positron. Now what the heck is a positron? A positron, pardon me, is kind of the opposite of an electron in the sense that it has no mass, but it has a +1 charge. Slightly different part. It's a new particle. Now one thing that I want to note here is that a neutron can actually spontaneously decay or break down into a proton and an electron. This happens quite frequently. A neutron spontaneously changes into a proton and electron during a reaction, and the proton gets added into the nucleus, whereas the electron is released, and you see a change. We'll see a couple examples here in the textbook, especially. The example problem 23.1 on page 989, which is one I want you to try. Don't try it yet, though, because I'm going to show you some examples that I want you to copy down into your notes. Okay, so here are some examples of radioactive decay. As you copy down these examples, it's also important to note that there are some rules that apply to these, even though they seem to be breaking some of the rules we've already talked about. Let's take a look at the first one before I get to the rules. The first example here. Notice they're all listed. We have alpha decay, beta decay, positron emission. There's all kinds of different reactions. These are just 3 different examples. You have alpha, beta, and positron. You could have other ones based on the other particles that we've talked about already. But here in alpha decay, we have an atom of francium that has a mass of 220 and an atomic number of 87. So that's what we're starting with. And it's unstable, so it's going to break down. And when it breaks down, it's going to break down into astatine 216-85. And that's what the major nucleus is going to be. Now, in order for it to do that, it has to release some of the particles that are already contained within the original nucleus. And it just so happens that in this case, the particle that is emitted is an alpha particle, which is a helium atom, or helium nucleus, I should say. So, here are the rules. The total number of protons plus neutrons in the products and in the reactants must be the same. Conservation of mass. That doesn't change from regular chemistry. So let's take a look here. We have 220 as our mass. If you look at the products, 216 plus 4, those two numbers have to add up to give me the original number in any type of nuclear reaction. The mass numbers have to add up. There's conservation of mass. The second rule is that the total number of nuclear charges in the products and in the reactants must be the same. So there has to be conservation of atomic number. Now note, 87 is the original atomic number. 85 plus 2 would give me 87. That's going to be the case in every single one of these instances. You can see for yourself. But those two rules are going to apply no matter which reaction we're talking about. Okay, so copy these down. There's an example of alpha, beta, positron emission, and if you have any questions about them, make sure you bring them to class. Here too are 2 examples of transmutation, which is the combining of nuclei or the bombardment of particular particles. So instead of releasing the particles are being shot at the nuclei. So in this case, a helium nuclei is being shot at a nitrogen nuclei. And what we end up with is an oxygen nucleus that has 17 mass number and 8, and we also have we were left with a hydrogen emission. So again, note that if I add these two numbers up, they should equal the same as these two numbers added up. 14 plus 4 is 18, 17 plus 1 is 18. 7 plus 2 is 9, 8 plus 1 is 9. I'm not breaking any of the rules, and the same should be true in the next one. Artificial transmutation is when we purposely bombard nuclei with particles. Now, nuclear fusion versus nuclear fission, right? And that's generally what we're talking about here. So, nuclear fission involves splitting nuclei, while fusion involves joining nuclei. Fission is the main type of reaction that occurs in a nuclear reactor. We take a nucleus and we allow it to undergo radioactive decay, and we take the energy from that. We use that to generate our own electricity or what have you. Both of these processes, whether it be fission or fusion, release large amounts of energy. Now you see I have a picture of the sun there. The sun, or any star really, are gigantic nuclear fusion reactors. Nuclear fusion is a lot harder to accomplish on Earth. We can only do it in very small quantities because it releases a large amount of energy. We haven't found a way to control it. We haven't found a way to make it work efficiently for us and safely for us. But when we figure out all the ins and outs of nuclear fusion, it could provide a really substantial and important way to produce clean energy. Nuclear energy is fairly clean, but you do have radioactive waste afterwards, which is not so good. Nuclear fusion would allow us to produce things that, and a ridiculous amount of energy, which would be clean compared to the way we burn fossil fuels currently. So there's a lot of science, a lot of emphasis being put on nuclear fusion as like the savior of energy. Although people tend to be a little bit intimidated by nuclear reactions overall because of the potential for catastrophes. That in a nutshell is your introduction to nuclear chemistry. Make sure you do example question 23.1 on page 989 and bring your questions to class.